Understanding the Ethernet frame. In this lesson, I'll be covering two aspects. One related to technical terms that everyone studying or working on networking should be aware of. And second is about the sizes of Ethernet frames. In my previous lessons, we have already discussed the different parts of Ethernet frame. They are DMAC, SMAC, type, data and FCS. The first three fields that are coming before the data field comprise of what we call it as header. So the header consists of DMAC, SMAC and type field. And if we add the length of these individual fields, that is what gives us the length of the header. So the header length is SMAC plus DMAC plus type size fields, which is 6 plus 6 plus 2, that gives us 14 bytes. And the purpose of the header is to convey the sender, receiver and the upper layer protocol information. Just like we have these three fields that we are now calling as header that come before the data field, FCS is a field that comes behind the data, and that is why we call it as footer. So the FCS field is what makes our footer, and the size of footer is 4 bytes. And then we can say that the purpose of the footer is to ensure data integrity during transit. So if you look at it, there are three parts in the Ethernet frame. Something that comes before data, and that is the header, and something that goes after data, that is the footer, and the data itself. And what exactly is data? It is nothing but the layer 3 packet that is being encapsulated. And this field can be called as payload. So anybody ask you what are the different parts of the Ethernet frame, you can call them as header, payload and footer. And then if anybody asks you what are the parts of header, then you can say SMAC, DMAC and type. The sequence does not matter as long as you know the different parts of it. So now that we know the header, the footer and the payload or the data part, we can say there are two aspects to the Ethernet frame. One is the data part and the other is the non-data part. So what is the non-data part? The header and the footer are the non-data part, and these combined together become what we call as that overhead. So anytime an Ethernet frame is supposed to transport a layer 3 packet, it will add a overhead. How big is the overhead added? It is of 18 bytes. And this is the non-data part. But can we live without it? Because remember, the aim or the goal is to transport the layer 3 packet using a Ethernet frame. But can we do it without the SMAC, DMAC type or FCS field? No, we cannot. So that overhead is required. Now, let me move on to discussing about the different size of Ethernet frames. When I am talking about different size of Ethernet frame, what I mean to say is that an Ethernet frame has the capability of carrying different size of packets. What packets? Layer 3 packets which are of different sizes, right? So the minimum size of packet that an Ethernet frame can carry, I am talking about the layer 3 packet, it is of size 46 bytes. So when let's say an IP protocol sends down a packet of 46 bytes, we add the 18 bytes of overhead, that is 14 bytes of header and 4 bytes of footer, and in all the total becomes 64 bytes. This is the minimum size of a standard Ethernet frame. Now by any chance, if the layer 3 sends a packet down which is smaller than 46 bytes. For example, I am taking an example of 30 byte packet here. This is 16 bytes short and this needs to be filled up. And how exactly it is filled up? It is filled up by adding zeros to it. And this process is known as padding. So whatever is the gap, fill it up using zeros, and this process is known as padding. And this is how we get our minimum 46 bytes of section. And this obviously gets converted into what we have been calling as data or PDU interchangeably. And then we have the normal header and footer added to it. And then total becomes a total of 64 bytes. By any chance, if an Ethernet frame is found which is smaller than 64 bytes, for example, an Ethernet frame of 633 bytes, then this frame is technically known as a runt and it is an illegal frame and should not be consumed. It needs to be dropped or discarded. Okay. Now pay attention that I had underlined the word standard. The reason I am saying standard is as when the Ethernet protocol was initially conceived and the standard was made at that time, the minimum size for the Ethernet was set to 64 bytes. Similarly, the maximum size for the Ethernet frame was standardized to be 1518 bytes. No rocket science in this. If you notice, the total is 1518 bytes. That should give you a clue that 18 bytes is what Ethernet adds as overhead. That means the layer 3 protocol packet should be 1500 bytes, and that is exactly correct. So visualize it as follows. And that is how we get a total Ethernet frame of 1518 bytes. Now, as time progressed, there were technological advancements and new implementations came. The Ethernet standard was further expanded and standard expanded to the limit that could accommodate packets which were bigger, huge. For example, maximum of Ethernet, the maximum that Ethernet frame could now carry is a packet coming from layer 3 of size 9000 bytes. So that is why we call the term jumbo Ethernet frame. So 9018 bytes is the maximum size for the Ethernet frame, and we get it when the packet coming from layer 3 is of 9000 bytes, like this. Okay. Summary points. Remember what exactly is the header, what exactly is the payload, and the footer. Remember the total overhead is the header and the footer combined, that is 14 plus 4, 18 bytes. The minimum size of a standard Ethernet frame is 64 bytes. The maximum size of standard Ethernet frame is 1518 bytes. Jumbo frames go to the limit of 9018 bytes. Remember, anytime a layer 3 protocol is sending a packet which is smaller than 46 bytes, we employ padding. And also, finally, remember the important term runt. Runt is an Ethernet frame which is smaller than 64 bytes.